Hey, Scott, thanks for joining me today. I thought we would get together and talk about the upcoming MBD GD&T class, master class, because you're the master, that we have offered this fall virtually.
That sounds great.
Great. Starting with the story of how we met. We just calculated, it was back in 2015, which makes that 5 years ago. Sort of ridiculous that much time has passed, but it has, because that's what happens with time. And I was thinking about the story and why did I call you in the first place? And it was because I had received a drawing that I was supposed to turn into MBD, and it had datum targets on it. And I, because I'm a spacecraft designer by trade, had always designed aluminum, brackets, orthogonal parts, traditionally manufactured, no casting, anything like that. And I went, well, I know GD&T, but I don't know what these datum target things are. So panicking a little bit, I was like, wait, I met this cool guy at the ASME meetings, and his name is Scott, and I think he lives in Denver. It'd be great if we could get together, back when we could see each other in person. And yeah, so do you remember that first meeting?
Yeah, that was great to see you doing the model-based definition, and which I see as a great logical step to this. I think it really created a good partnership.
Yeah, and we kind of after that first partnership, we went, hey, you want to work together on making a class where we could do this together? Yeah, so, and it's turned into our modern GD&T 4 model-based definition class, and you and I used to teach it, and Ryan taught it, and now we have Dan Fury who's teaching it, and he's kind of taken it to the next level and evolving it.
Yeah, I think it took some time to collaborate on material and get everything dialed in, but I think it really is meshing well. And take the full geometric tolancing concept, and the next step is going to be putting it into the model and have it machine readable. I think that's great. And I think our ideas on how we apply GD&T and how that would work in the model, they work very well together too. So I think it's been a good partnership together.
Yeah, and super fun. And we've learned a lot from each other. And I do know what datum targets are now. So that's good. Well, great. So we made this class specifically because you and I worked for a customer and they really wanted to share kind of the modern or the evolved way for that ASME Y14.5 has evolved to with their leadership, because very smart leaders, right? And they used to be MBD practitioners. So we created this master class. Can you tell me more about what you think we're really trying to drive home with that master class and what problems we're trying to solve?
Yeah, I think it's really about modernizing your GD&T approach. I mean, the original GD&T system that was developed in the 1960s and 70s and all the way up to the 90s, they didn't anticipate it going into models. They thought of it always being just a 2D drawing based method. And so all the definitions in those 94 standards and earlier were all just for paper drawings. So it was 2009, 2018 standard Y14.5 that they said, well, how do we actually do this in model based? And so they had to modernize and just kind of tweak the definitions and adjust the symbols a little bit so it works in that model based environment. So going full geometric tolancing on things and eliminating a lot of the ambiguous plus minus tolancing that you always needed a human to step in and say, oh yeah, that's what this means. Now, since it's going all machine readable and model based, you need to eliminate the plus minus. Position profile tolerance as the main way of defining our features, and having a proper datum reference frame. So having a coordinate system established that is mathematically defined. That's, I think, the big takeaway is full geometric tolancing with a datum reference frame.
Yeah, and you bring up that word full, which of course we know in MBD land is a bit contentious because I think when we go model-based definition, there's a big fear factor that we are losing information. Which I think is very natural, but there are things that we have to shift our thinking about, and I think that's what this class is about: is learning to shift your thinking from, if you hear the word full GD&T, what does that mean? And I liked what you said about removing the ambiguity, There's drawings today all over the planet that are ambiguous.
Yeah.
Yeah. I mean, hey, let's talk break edges. It's pretty ambiguous, actually,
Yeah.
right? Not mathematically defined.
Yeah, just take a dimension, you put a dimension with a tolerance, and then you say, well, is that this feature moving like this or this feature moving like that? It depends on your perspective. And so switching from that dimension-based tolerancing system, which is very drawing-centric, to feature-based tolerancing, which is very model-centric. Every model has features. I think anybody who's working with a CAD system understands that. So it makes sense when you go full feature-based tolerancing with geometric tolerancing.
So Scott, in this masterclass, what are the key concepts that you're trying to convey to the students or the attendees?
I think the key concepts came from what are the big problems people have from going from a drawing-based tolerancing system to the model-based. And I think it comes from ambiguous plus minus tolerancing, so removing that and moving towards position and profile for pretty much all of our features, and also establishing a proper datum reference frame. Sometimes we see datum feature symbols on center lines and things that don't make mathematical sense. So we got to recenter people on how a proper datum reference frame is established on the part, and then position and profile all ties into that. So those are major concepts, I think, is position, profile tolerancing, and then also the datum reference frame.
And that leads me to, I'll bring up my little part here. This is one of those parts that you and I've worked on together. Real part, something I might have made in spacecraft design on a bracket. In fact, I was thinking it was kind of like embedded in a like a composite curved surface or something, which isn't obvious because it looks planar. We've talked about this part in particular, and I thought, yeah, I know, I got it. I got the datum reference frame. It's no big deal. Like it's this and it's this and it's, oh, maybe it's this whole, right? Because that's what the linkage is and stuff like that. So can you talk me through maybe what some of the common mistakes are around that?
Yeah, I think sometimes what people want to go for is they see whatever's the nice big flat edge. They said, is it flat? Is it perpendicular? And those are the features that I want to go with. But really, it should be the functional features. How does it fit? How does it mount in the next level? And even if that feature could be a little bit crooked or curved, like your example, we can still use them. And mathematically defined surfaces actually become a lot easier when you're using model-based definitions. So it doesn't always have to be that biggest, flattest surface, but what are the functional features that you care about and how it actually fits in the assembly? That's what we're going for our datum reference frame.
Yeah, and I can't count how many times I've said, hey, Scott, help me with this example. And I give you one part and you're like, that's nice. What's the assembly? And right. I mean, there's probably email chains we can go find where you said, yeah, Jennifer, I need the assembly. So I'm starting to get it, like datum targets. So I think one of the big aha moments for me was it wasn't just about this part in its own, sitting on a table. It was this part in the context of the assembly, and that's how we established datum reference frames. That was a really big deal for me to understand.
Yeah, so often I notice that people just want to pick the largest face is A, the next longest edge is B, and then some side edge is C, but not really thinking about how the part functions or how it fits in the next level. And so part of this class is looking at a functional datum reference frame. How does this part actually fit? How does it mount in the assembly? And by dictating that with your geometric tolerancing, you can communicate better how the part works. And if somebody knows how the part works, in theory, they should be able to inspect it better and manufacture it better.
And I'm so glad you brought up manufacturing and inspection, because one of the big wins and the big return on investment for model-based definition is about how do we streamline operations in manufacturing, and how do we get quality to not spend all that time ballooning drawings and rather we give them a really solid bill of characteristics. That's the hard requirement that then they can take, provide validation results of those requirements to determine if it's in or out of spec.
Yeah, it used to be with a 2D drawing, you would put something down, and if it was close enough, it was probably fine because an inspector or a human was always on the other end of this who could interpret it and say, okay, I really know what they meant to say. But with machine readable capability, you really need to make sure your GD&T is exactly correct. It has to be mathematically sound, or the computer is going to have a lot of pushback on it. So getting that semantic GD&T correct so that either a human or a machine can read it is really helpful. And now these things can be auto bubbled too. So the characteristics can be bubbled, and then it saves you hours on inspection time too, the CMM programming, because the bubbles will correlate directly to that feature. So feature-based tolerancing will really solve a lot of our problems that we had with the old 2D drawings and streamline a lot of our inspection.